Yeah, recording has been started.
Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the 21st Centenary Lecture under the Centenary Lecture series. Today's lecture will be delivered by Professor G.K. I'm really sorry. Yeah, today's lecture will be delivered by Professor G.K. Ananthasuresh. He is a professor in the Department of Mechanical Engineering in IISc, Bangalore. Today's session will be chaired by Professor Shishir Kumar Guho, former professor in the Department of Mechanical Engineering, IIST Shibpur. Sir, over to you.
Professor Go, please. Sir, you are muted, I guess.
SKG, please unmute yourself.
Now it's okay.
Yeah,
Today we have Professor G.K. Ananthasuresh with us as speaker. Prior to his lecture in this session, let us first introduce him to you. Professor G.K. Ananthasuresh obtained his bachelor's degree in mechanical engineering from Indian Institute of Technology, Madras in 1989. He obtained his MS degree in mechanical engineering from the University of Toledo, USA in 1991. Subsequently, he earned his PhD degree in mechanical engineering from the University of Michigan, Ann Arbor, USA in 1994. He then joined as a postdoctoral research associate in Massachusetts Institute of Technology, Cambridge, USA. Later on, he served in the Department of Mechanical Engineering and Applied Mechanics in the capacity of an assistant professor and associate professor in the University of Pennsylvania, USA during the period from 1996 to 2004. Professor Ananthasuresh is currently a professor of mechanical engineering and the Dean of Mechanical Sciences at Indian Institute of Science, Bangalore. He is an expert in topology, optimization, compliant mechanism, and microelectromechanical system. His research interests also include kinematics of mechanism, mechanics of biological cell and biomedical devices, and microrobotics. In addition to 2 test books and 4 edited books and 15 books chapters, he has published more than 300 journal and conference papers and obtained 16 patents to his credit. His research is funded by the government agencies and industries, and his research work is recognized with 15 Best Paper Awards, 10 Design Prizes, Early Career Award of National Science Foundation of USA, ACES Ralph Teeter Educational Award, Sharno Jayanti Award, and Shanti Swarup Bhatnagar Award, and Abdul Kalam Technology Innovation National Award in India. Professor Ananthasuresh is a fellow of the Indian National Academy of Engineers. He served on the editorial board of several national and international journals. He was also appointed for the visiting faculty positions at several national and international institutes of repute like Catholic University Leuven, Belgium, University of Cambridge, and IIT Kanpur. Professor Ananthasuresh has a distinguished academic profile with the extremely remarkable achievement in research. Now, please welcome Professor Ananthasuresh to deliver his lecture entitled as Positive Outcomes with Negative Stiffness in Mechanical Design. So I request Professor Ananthasuresh, please start, and time is allotted 45 minutes around.
Thank you, Professor Guha. And I'm just sharing my screen. Is it visible now, the screen? Can somebody confirm that it's visible, the screen? It's blank white now.
It's a blank white.
Yes. Okay.
It's white.
Yeah. Thank you, Professor Guha, and Professor Sudeep Ghosh and IIST, and all the distinguished uh, people who are in the audience today. First, I would like to start off by expressing my hearty congratulations to Mechanical Engineering Department at IIEST on its centenary. And these are wonderful series, and I have heard the earlier lectures that are there, all listed on your website. And I see that except one or two, all others are distinguished alumni of your institute. So I feel deeply honored that I'm invited to give this lecture. It's really a privilege. Thank you very much. And since we're talking about Centenary, I would like to indicate the years of my institution, Institute of Science, which is 112 years old, and Department of Mechanical Engineering, where I am in, is 77 years old. It's younger than your department by almost a quarter of a century. And our lab, which we call M2D2, is 18 years old, much, much younger. But I've had wonderful students who did a lot of work in this. And we chose this name, which sounds odd, somewhat reminiscent of R2D2 in Star Trek or Star Wars. That's intentional. We want to excite the students with something that is futuristic. And it stands for Multidisciplinary and Multi-Scale Design and Device Laboratory. And you would probably see why it's multidisciplinary and also multi-scale. And of course, we do mechanical design. That's at the core of what we do. And we also make a number of devices. I have a lot of videos. Anytime it's not playing well, please let me know so that I can actually switch to another network, which probably will be better. I chose this topic. There are wonderful topics in these earlier 20 lectures that you have had, and I really list all the topics. And so I chose this title just to match the kind of titles that other people had used. So just to say that negative stiffness, what can you do positively? And as I said, this work was done with numerous students, almost over a decade, actually. And also the funding from several organizations, DST, ISRO, INAESCRB, RGUHS, which is Rajiv Gandhi University of Health Sciences, and companies as well, Eaton, India, as well as Toyota North America. So what is this negative stiffness? So let me begin there, and later we go to positive outcomes. So we are actually trying to turn something that is negative to positive here. And one thing that, as a mechanical or structural designer, we dread is elastic instability. We don't like it because that's considered like failure most often, not all the time, most often. But then we don't need to look at it as a failure mode if you can exploit for something that is good. So since it's evening, there is nothing wrong in remembering somebody like Charles Dickens, who said, suffering has been stronger than all other teaching and has taught me, he says, to understand what your heart used to be. And this is the quotation that is often used. I have been bent and broken, but I hope into a better shape. So that better shape is what I'm taking here. In fact, we work on compliant mechanisms where Professor Steve Vogel, who is a very distinguished biologist who wrote about mechanical things. I'm sure many of you have read his books and papers. He had his article written in 1995, just when I finished my PhD, Better Bent Than Broken. That had a profound effect on how I started to look at mechanical design, where things can bend, but they do not break. And they bend into a shape that is actually useful. So its inspiration comes from Charles Dickens and Steve Vogel, and of course, many other mechanical designers before me. So buckling of columns is known to all of us. So this is an instability. And there is a little problem we always start with just a rod, rigid rod, not a flexible column, a rigid rod which is pivoted like an inverted pendulum, and there is a rotation spring with the stiffness kappa. And if you apply an axial load after a certain value, which is P critical, it actually will have equilibrium, that is stable equilibrium, that will be off from theta equal to 0. One can derive the critical load very easily from looking at this equation and looking at stability and say that critical load in this case will be kappa divided by L. Okay, that's a wonderful little problem that we can first start to look at instability. And this is a very rich problem because we can illustrate the bifurcation. So theta equal to 0 will be solution for certain value of PCR, P critical, and then it bifurcates and then bifurcates and bifurcates. It just goes on, right? If you keep increasing the value of P. But then we also learn in thinking about buckling that when you have a little bias right from the beginning, it will actually take a very nonlinear force deflection path. Here, P versus theta. So it's a very rich problem. Most of the time, we design structures to avoid this type of buckling. So, but today we are going to see how we can take advantage of this instability. So here I have one first video. I hope it plays for you. It's a very slow motion video. All of this happens in a fraction of a second, in a few microseconds actually. It's a high-speed video slowed down. We're just pushing an arch, which is a shallow arch, which is pinned at both ends. And you can see after a while when we are pushing, it lost contact with it and just moved by itself and then stayed there. Now, this is in another stable state, of course, compared to the earlier one, which was a stress-free state, whereas this one is a stress state. So if you want to get buckling, you can always preload it and achieve buckling. But here, we try to make things that are stress-free initially. And then when we push it, it will go to a stressed state. So now, what is this concept of negative stiffness? So let's look at the force displacement profile that is shown in this slide. I hope the slides are changing fast enough. And the force deflection graph, I've also put energy versus position graph. So we know that this ball and a hill analogy, when it is rested very carefully at the tip of the hill, it's unstable. Whereas at the bottom of the valley, it is stable. So here it is bistable. You can get any number of stable positions if you design it to your taste. But this is a bistability where you have two valleys, two minima in the energy curve, and also one maximum. And here you have very nonlinear force versus position or force versus displacement. This is the kind of behavior we just saw in the video that I played. Now, the two stable states you can see for the pin-pinned shallow arch. And sometimes it can also snap through. That is, it won't be bistable. That is, force will never become negative. It will stay positive, but yet you get this nonlinear profile. There'll be a force goes to a maximum and then comes down to minimum and then goes through, which we call snap through. And then, of course, bistability you already saw. For these two, if you notice these portions that I have marked in red now, that portion is negative stiffness. That is force versus displacement. If you take the slope, that has negative slope. That is when displacement is increasing, force is actually decreasing. This can be thought of as a static response, force versus displacement, where you're holding it at different positions and what is the reaction force? That's what I have plotted. That region is negative stiffness. And that is actually the source of instability here. It just snaps to the other case or other stable position. But then if you do controlled way, you can actually get this negative stiffness zone, and that can be exploited as we will see today. And some of you might have seen it earlier also. How do you use this? Both this bistability as well as snap through. And we have been working on this for over a decade. Actually, I didn't realize that we were working on it for over a decade. And a number of applications have come through. Some of them are shown here. They are micro machine bistable switch, a circuit breaker that every house has, and a therapeutic footwear, and a chair for the elderly and people who suffer from arthritis and others. Also, valveless pump and mechanical logic gates processor, which is special to IIST. I'll come to that. And that is your institution. I'll come to that. Also, a compliant gripper that is kind of a universal or versatile, and something that we do with biomechanics of cells. But that I'm not going to talk about that. Whatever is I put in black color, I'll talk about that. There's one in blue color, passive vibration isolator. That's actually not our work. It's a company called minus K. Minus K itself tells you that K is stiffness, minus is negative stiffness. A lot of application can be thought of. And I'm going to talk about, if I talk about in detail about each of them, it'll be a talk in itself. So what I'm going to give you an overview of this and how we are exploiting negative stiffness in all of these applications. So it all started with this click-clack tin lid. In fact, I have it here with me, and this I got it in 2002, actually 20 years ago, at a conference where they give some goodies with some candy in it. Somehow I liked the sound of it and the way it works. So I kept it with me, and then 10 years later, I found use all of a sudden, and then another 10 years we have worked on it. So the way it works, it's just a rusty metal, tin. So if you press on it at the top, the concave surface, convex surface becomes concave, and it opens this lid. They go outwards radially, and then when you press on those from the side, it actually flaps back, and then it makes the sound click, 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 clack. So this was interesting. So I always used to play with it. But then one day we started, I'll play it for you, because if I were to be there, you would have seen this. You can't hear the sound, but you can see how you can flip it back and forth by pressing at the center and pressing on the sides. So I'll play it again. So if you press that, these things come outward. You can take the lid out on the tin, and then when you press it, it'll press it again. So it's a bistable, in fact, bimodal. That is, you can do it in two different ways, where there are two pathways to switch between two stable positions. It was intriguing for us. And then we try to model it. So if you look at the same force versus displacement curve I talked about, if a shell is convex up like this, that's where you are. At maximum, if you go, then you are actually pressing on it from 0, you go to the maximum and then switch to the negative stiffness and comes to the other stable position where there is no force again, force free, it goes to the other state. So the shell is what we try to model. It was quite interesting when we tried to model it. And I was playing with this rusty thing for a long time, and a parent of one of my students actually found it somewhere else and gave me a nice looking tin. And there are people who make these just to give as gifts, like I got it at a conference 20 years ago. So we took this shell, we were analyzing it. There were some interesting things. Then we thought we really want to analyze it well, analytically. Then instead of doing computationally, we took a section of it. That became a shallow arch that I'm talking about. It's a pin. That condition is important for this to work because it actually rotates around the periphery, the shell. So when we took a section of it, it became a shallow arch. So I'm showing the first equilibrium state, which is stress-free, just pinned at two ends. And then when we apply the force, it goes to the other state. And that's a second equilibrium, no force, but it's stressed. That's also stable equilibrium, as you saw. If I just were to rotate that half of it about that pin joint, shape will be different as it is shown here. Because the shape is different, it's deformed and it has stress in it. So here I have again showing that actuation. There are two ways of actuating this shallow arch. One is at the center that switches from state 1 to state 2. And then the second one where we are applying torque at the pin joints to switch it from the state 2 to state 1. There are two actuation modes. That is interesting. And you can see how we actually switch here in this video. I hope the videos are playing well. So here we are actually actuating by applying torque rather than applying the force. There are actually umpteen ways you can do it. I'm just talking about two ways of doing it. And here also, if you start applying the torque, at some point, your thumb that is held now, it will lose contact. It just goes by itself. Then it happens very quickly. That's why I have to do high-speed video and slow it down by putting markers and what's happening. If you look at this from the energy viewpoint, we can look at the potential energy that I showed earlier. The moment we apply some force, you add to the strain energy also the work potential, and the energy landscape changes. That's what I'm showing here. Potential energy without the force work, that's just strain energy. When you apply with port 1, that is applying the force at the center, it has one kind of a curve, that is dotted line here. And then when you apply the torque at the hinges, it's a dashed line. As we're doing it switches, energy landscape changes. We can see it. I will show some simulations later with time, how they look at, how they would be. And this click-clack tinlet actually takes a very tortuous path, as I'm showing, A to C, and then C to B, and B to D, and D to A. And that's interesting. And in fact, one can play with this in many other ways and use it in different applications. We first modeled it using just a rotation spring and translation spring and try to understand with simple algebra. So how we can get this critical forces that are required to switch it from state 1 to state 2 and also from state 2 to state 1. So there's all simple analytical algebra, I think, just to understand. Then this video will show you how the energy landscape changes as you watch the force versus displacement, also how the energy curve is changing with time as I'm applying the force. That force changing with the displacement. There's a midpoint displacement of the arch. U mid is a midpoint displacement. How it goes and settles at the other stable state. And then while coming back, as you can see, because it is stressed, it requires much less force compared to the force required to switch it from state 1 to state 2. State 2 to state 1 is very little force. The energy curve also has this local minima that's as the ball is moving that is there, but that is very little compared to the previous one. That is a slope. That's where force is much less. You can switch with much less force from state 2 to state 1. So it was interesting. It was a curiosity exercise about this click-clack lead. But then we thought, can we use it somewhere? And that's when we started on this project of making an assistive chair. So if you imagine that arch that I just showed you, when the person sits on it, the convex up arch can become concave down, just like we saw. Okay, and then if the person wants to get up from the chair, rise from the chair, they can, the person can press on the armrest. That is like applying torque at the joints. Then it will go to the other state. It will give the push for the person to get out of the chair. Of course, because the other state is also stable, while you are sitting in it, you don't feel any push. It will be comfortable like a regular chair. When you press on the armrest, it will propel you up. Of course, we don't want the person to go like a projectile because this is an unstable phenomenon. So if it just goes like that, it will be a problem. So we started combining this with static balancing so that it will be slow and gradual, so that the person using this chair would not feel this sudden motion from sit to stand and stand to sit, both ways. So we had this finite element analysis just to see how we can use this two-port actuation to go while sitting, it's stable. So you are comfortable, it's not pushing you. When you want to get up, you press something, give a trigger, and that pushes you. But then static balancing combined could do this. So when you started thinking about it, then the design came up. How do you design these arches that are bistable for this application? We looked at this force displacement curve and thought, okay, there are switching points. Okay, there is first switching point and switchback points we need to have. And then the switching forces, for shifting it from state 1 to state 2 and then back. And then how much travel will be there. And what is the range of displacement where you have negative stiffness, because that we need to really tune there. Also time to switch from state 1 to state 2 and state 2 to state 1. All of these we wanted analytically, because doing it computationally is an unstable phenomenon. So if you use finite element analysis for the shells or arches, it takes considerable time. You can do it considerable time. Any design thing that you do will be problematic. So we started looking at it analytically. So I'll just go over the analytical modeling quickly. And when you start looking at it, you trace it to the really stalwarts. In this case, it is Professor Y.C. Fung. He is the father figure for biomechanics field. It was probably his doctoral work, wonderful piece of work at Caltech, where he had looked at this shallow arches, how to model them. At the same time, there was in naval research, the Office of Naval Research, other people, this Hoff and Bruce also had done it. In fact, they had acknowledged that, just, before they published, Professor Fung had and Kaplan had done this also. So it's a, coincidence, 1951 is when did this work. And that's what people still use today. Their technique was very elegant and very simple. And what they do is, I'm showing two rotation springs because we can have stiffness there, but their original analysis was simply pin. What they did was, you take the shallow arch that you want. Instead of that, if you imagine a straight beam between the two hinge points, that will have some buckling mode shapes, right? They took those buckling mode shapes and expressed that height of that arch in terms of the buckling mode shapes of the straight beam there. And they did the same thing for the displacement also, where the arch deforms, right? Deformation of that arch, W of x, that also they expressed. There is small aj, 1 to infinity. You can take as many modes as you want. They can model the arch itself. And then the displacement or deformation of this arch, which is W in the transverse direction, will be capital AJ. That's what they took. That was very clever, because then depending on your need, you can take first 2 modes, first 3 modes, first 1 mode, 2 mode, whatever, right? It gave them a continuous problem became discrete. That always happens in the modal method that we all know about. But the other thing that did was, of course, all these mode shapes can be worked out very easily for any boundary condition, pin, fixed, or whatever. That's all easy. Once you have these mode shapes, you will know for a given profile what is a small a. That is small a1, a2, a3, whatever you have, you can get the shape. And you can make the higher ones 0 also, depending on what shape you want to have for the arch. And then, of course, deformation you have to compute, which is W of x. And here is where their genius of that paper, those two papers came through, was instead of solving this differential equation, which is quite difficult to solve analytically, so they use the energy method. They minimize the potential energy by writing that the bending energy and also axial compression energy. Bending energy is easy because we learn it at the undergraduate level. Axial compression energy is more difficult, but they had a very clever trick. All they did was they took the axial stiffness and then change in length of this arch, because as the arch deforms when you apply the force, the length of the arc length of the arch will change. They just took that original length and the final length, change in length minus original length, that basically change in length multiplied by stiffness, average one. It works wonderfully. It actually gives results that are very accurate with finite element analysis. And why it works, we still don't know, but it works wonderfully. And that's what they had done. And you take this potential energy approach, and now it becomes easy to do optimization. Basically, you have your W has this capital A1, A2, A3, which are the mode weights of all these different buckling mode shapes, and you can determine them analytically very easily. And that's what we are doing here. And then you have boundary conditions also added, and you can take the strain energy and the work potential and the compression, bending as compression. You can write all these things in terms of W, but W is not a continuous function now because we have mode weights, right? So that becomes very easy. You get equilibrium equations. If it depends on how many modes you take for W, and you get so many equilibrium equations, you can solve very easily. Everything can be done analytically. And this is what my former student, Dr. Safwan Palathingal did, who is now faculty at IIT Hyderabad. It is his work that I'm presenting mostly today. And he came up with this analytical way of computing the critical points. What are the red spots here? So that we can get it very easily for different boundary conditions and different number of mode shapes that we consider. And it's all analytical. We can derive formulae for these things. We don't do finite element analysis. We can change the boundary condition by putting a spring and so forth. So it's all analytical and quite straightforward once you learn from the masters. And then we also found out that instead of letting this arch deform in a plane like I showed, if you let it go spatially, spatial pathways, that is, now you also introduce twisting, because we saw that in reality, the force required for the spatial pathway, the switching force, is less than that of planar pathway. So what you see, planar deformation, actually the green curve, it's a higher switching force than the spatial pathway. In reality, when you have a structure, it always takes the least path of resistance, right? So it actually deforms also, like twists. So it's interesting. So here we could also include the twisting energy. Interestingly, this analysis was done by Saint Venant and Mitchell. It was in the Theory of Elasticity by Love, which is a classical treatise on elasticity. They had not included the twisting energy. We put that term, Safan added that term to the strain energy. They were able to do it also analytically, the spatial buckling also. We started becoming more and more courageous to look at these things. Then we started looking at synthesis. How do you come back? That is, if you want certain bistable behavior, let's say if you have that h of x, which is the undeformed arch, and deformed arch you have, that is h plus w, where w is the deformation, then you have two stable states. How do you relate them analytically? It was possible because of the method I just described. So if we are given this small aj's, how many ever you have to define your shape, from those you can actually get capital aj's and go back and forth. It was all done analytically. So those are the equation I'm showing. A lot of algebra, I'm skipping all of that. So if you are given the stress-free state, that is ai's, many of them can be zero. You may have only one or two or three or a5, a7, whichever to our need and taste. And then it was reduced to a single nonlinear equation in A1. Capital A1 is the deformed shape. And then once you have that, everything else we calculate analytically. Simple formulae that Safwan was able to obtain here. And also the other way, if we are given the stressed state, you can get the stress-free state. That is basically for design, this formulae become very handy. So you can actually design the undeformed state of the arch for a desired deformed state. That's what you want, and you can get that using this formula. So we started doing all kinds of shapes. You could specify, since analytical, very easy, only one nonlinear equation in one variable, we could do that very easily. So with that analytical design for different boundary conditions, for example, if you want to make a valve, no, it is not a valveless pump I'm talking about, just a valve, that is a shape that you want in the stressed state. That is the other stable state, not the one they are making. So how do you get the first one? So we could get it from this analytical formula. The red one that I'm showing, if you apply the force, it actually becomes almost like this, which is shown here. If you put two arms like that, you can also grasp something. So by looking at these, we started getting a lot of ideas for applications. So I'm looking at the clock also. So I'm going to show a lot of applications now so that we can end the talk. So I'm going to go fast. Now that I've described the concept and the analysis and synthesis equations, so micro machine switches. So this was funded by ISRO and a number of students. Giridhar, a scientist in ISRO. This is the bistable switch. It's a two-terminal switch. By that, what I mean is we have all seen lights where you pull a rope, light turns on, you pull it again, it turns off. Similarly, if you have two electrodes, two terminal switch, if you apply 5 volts, it will turn on. If you apply, let's say, less than 5 volts, it will turn off. So it's just two terminals, which ISRO team told us that it makes power electronics easy. They gave all the specifications. We made that switch using this negative stiffness and these arches, so several of them. I'll just illustrate the principle of how this works with the little first graphic animation, and then I'll show the real device also. So now the current is going from I to O1, and then when I apply this thermal electrothermal actuators, which are shown where I'm applying voltage, it will switch. I'm just showing intermediate state. It will switch there to the other state. And then when I apply the same voltage at the same two terminals, now you see I don't need to apply the voltage. I only need energy to switch from state 1 to state 2. In between, I don't have to. That's why that's electric switches. All the principle is there. We all know. And in this particular case, to switch antenna, they wanted a number of switches. They don't want to use energy all the time. Just switching use energy. That's why they were interested in. We pursued this application, apply the voltage, and for this we had to design a special actuator at the other end so that it actually switches back. So that's how it is. So I'll show the video now. Video will start playing. You see, it's a micro machine version. The beams here are 5 microns in wide, and thermal actuator is there on left side as well as right side. It's a particular reason why you need two actuators here, because we want to control the instability of it, because it's all negative stiffness in between. So we were able to make it, and it's a switch. And my student Dhananjay, put his imprint also, DJ there. So next, mini circuit breakers. They're wonderful devices, but they have many parts. Every house has this now, MCBs as they are called. They have a lot of parts. So Eaton Company, when we were talking with them, so we can do it, in fewer parts, actually 1 or 2 parts we promised them and did it. So that's how MCB looks like. It's a switch, but it has a lot of functionality. It's quite an interesting device. You can do manual closing and opening if you want. It can trip when there is a fault in the line, or if it gets too hot, it can also trip. Also, we should be able to relatch. Whenever there's a trip happens, we know that become loose. So you have to push it back and bring it down. All of it is mechanically, right? It's a wonderful device, but a lot of parts, as you can see. We started doing that with actually one part also we had designed, but then when you actually go to industry and then give them, they say that, oh, it's difficult to make, or they have to change lots of things. We gave them like 2 parts. So I'll show this device. It's a prototype, real size of this. We could get all those functionalities. You cannot see the negative stiffness here. It's hard. So with the details, you would be able to see. And this is another model. Instead of MCB, they had also MCCB. This is molded case circuit breaker, a little bit more. If you notice this video, after you do the actuation, I'll play it again. Yeah. After actuation, it waits for a while and then switch goes. It's like a delay. You can get delays in mechanical systems. This is one of those examples. So here we made a one-piece design of a snap action device. I hope the video is playing for you. After you move the switch, which is what you're doing in MCB, it waits for a while and then hold all the energy and suddenly go and snap, so that it make a very good electrical contact there. So that's how we achieved, and this is a 3D view of that device. It just, we put the MCB switch. It's all barring 1 or 2 hinges there. Everything else is compliant, and a lot of arches are there with these negative stiffness elements. There are a lot of detail, but I've already given you the idea of how we are doing analytical as well as synthetic modeling. Now, this is another application. This is footwear. We were just talking with a podiatrist, and they were talking about offloading. They always work with some memory foam or some other polymer material, which can be carved and shaped to suit the foot needs, where ulceration occurs or not. But then doctor told us that, after they use it for a few days, sometimes, even few days, their gait changes and some other portion that is not offloaded becomes vulnerable. So this was done with support from Rajiv Gandhi University Health Sciences, with Dr. Pawan Velahalli and my students Priyabrat Maharana and Jyoti Panavane. And normally you see static offloading, as it is called, where you basically carve out the foam-like material, but then that only offloads only that region for that time. When you change it, it will be a problem. Somebody came up with a electromechanical device where there are little pegs that move up and down. There are sensors, and they will go down and kind of offload, like I'm showing in the lower left half of the screen now. The dynamic offloading. We thought, can we not do that with entirely mechanical means using these arches, as I'm showing here? And the next video will also illustrate the thing. Again, we work with these arches, design them in an array of them, as you would see in this video. I hope again the video is playing for you. There are these snap through arches now. They just go down offload at a pre-threshold, 200 kilopascal. They use Pascal units for this podiatry. If it exceeds that, the arches will move down automatically. They snap, and then the load will go to another portion. And then we redistribute the plantar pressure. And then nowhere on the foot, the pressure will be more than what the doctor prescribes. And it can be customized to each individual, because we can make these arches, an array of arches throughout different regions of the sole of the foot, and different phases of gait, heel strike, flat foot, mid stance, heel off, all of those things. Normal footwear will have problem. The red spots are high stress. Static offloading, somewhere they offload it. Other places in the gait phases, different phases of the gait cycle, pressure will again increase. Whereas ours can be designed so that nowhere the pressure is more than 200 kilopascal. That's what we did. We did actually the tests in the lab with these measurements in the Karnataka Institute of Endocrinology in Bangalore, measured with about 100 people, and then arrived at the values, and so that we could design our arches. And some statistical analysis also. I'm not going to details in this talk. I'm giving an overview. This is how it looks. This is the hand my student is Priyabrat is doing, how it offloads. And today we have the footwear that looks like this, where you can step on it. It's all 3D printed, customized for each individual. Polyurethane seems to be very strong material, so we're not worried about this breaking. And this footwear can be now worn, and we can put sensors to measure pressure also, but we know that they snap at the prescribed or bespoke value. And we found that with this footwear, 34% reduction can be obtained on average in the entire gait cycle. You can walk, run, nowhere it will be more than that 200 kilopascal that you would do that. So these are just an insole that goes into normal footwear. The height of that thing is little more, the doctor says, but we're working on making side view. If you look at it, when I have arches, there are arches underneath and it can be slipped on and it works. It's actually prophylactic in the sense that it could change with the gait, and it'll what goes down and what comes up is actually controlled by the walking style. And through the entire process, it will not be more than what it is designed for. And we started with assistive chair. So I'll just go with that application very quickly. And this actually went on for a long time. Now we have a startup company, and all these people, geriatricians we talked, so took their inputs 10 years ago. They're still involved with us. And several of my colleagues and several students, several generations of students worked on it. It's a very simple thing. The chair is the seat at an angle, and there is a rotation. Here, with our ability to handle shells as well as arches, and twisting, bending, axial stiffnesses or energies, we're able to design a chair like that, which looks like as if you put a pillow. Some industrial design students did that. If you sit, it'll give you supportive force while you sit, so that you don't need to slouch into the chair, which normally senior adults tend to do. When you want to get up, while you're sitting, you don't feel anything. It's like a normal chair. When you want to get up, unlike what you need to press, now we don't have to do it. It itself will push you gently when you show the intent to rise. So there are a lot of work has gone into this, and this became a like hinge mechanism, we call it, using open section shells. And the easiest way is to show you the video. So you have, it's a compliant one. There are no bearings. It's just the whole structure, is flexing, twisting, and bending. And the open section shells, analytically, they're very difficult to do. But then my students worked hard and came up with interesting design methods that we could use to design these shells. And this is how it looks. But I think I have a 2-minute video that will show how the torque will rise first and then becomes again decreases. So negative stiffness there. That's when you kind of go into the chair. While getting back, it follows a different path and works. And we have done it analytically also, simple models first, and then finite element analysis as well. And we have a nice design method with which you can actually choose the torque versus angle, which is like a bell-shaped curve. And for sitting in and rising, it's two different curves. And we do that with a cams. I'll play this video. Hope we are able to see. And I'll be done in a few minutes after showing some more applications. Everybody knows that it's difficult to rise from a chair for people, especially the older ages. So we put first these EMG sensors to measure what is the knee torque. That's what you wanted to reduce. That's how it is when you don't have anything to assist. And when you get up, it'll be a different EMG value that you get. But now with the chair that we have designed, everything is inside, of course. There is a patent and a number of papers. It looks like this, metal shells there. When you sit there, and torque versus angle, you see there is nonlinear negative region. It's nonlinear negative stiffness region. That's for sitting in. Going up is different. Both ways the slopes are zero, meaning that neither case you don't feel that push when you are sitting there. And it all is one piece compliant design. And the virtual axis, the hinge is a virtual axis. It's not, you don't need bearings there. And the normal assistive chairs will have just a linear one. Most of the things that will have, it will keep pushing you when you sit, whereas here it doesn't do that. So, and it can be customized, as you will see in a minute. There are basically two cams. These are shells that twist and bend at the same time. That's what gives this nonlinearity that we are designed. and those bending of the shell can be controlled with cams. The little pieces that can be put, and we can customize this curve for every individual. They based on their weight, height. These are the cams. These are mechanical design talks, so cam must be there. This cam can be changed in this mechanism to suit different weights and heights and their ability. So of course, my student is sitting in it because we need ethical clearance to do that, which we have now. We tested it also. Those cams, how it moves over, that's the only kinematic pair there. Otherwise, everything else is compliant. I hope you got a feel for that. I will go very quickly a few other applications just to say how much is there that can be done with this negative stiffness phenomenon. Valveless pump. In the interest of time, what I will do is I'll just play this video. That it will tell you why it is valveless. We have the shell. We are, of course, we are doing a cross section here. The way the shell is made to deform asymmetrically will close in a cycle, input and output, they're all marked. How it closes the inlet valve or outlet valve, this shell itself closes. We don't need any valves here. And it can be done at very high speed, and a pump can be made. So this is something that we are actually working with Toyota Corporation, because they wanted very compact pumps. They can be almost like a flat, not bigger than the tin lid that I showed. Those shell can move up and down and close the inlet outlet valve in different phases of this cycle. Both sides are being utilized for pumping. There are two inputs, two outputs, in the sense that both inputs can be connected, both outputs can be connected. I hope you got the idea for valveless pump. And mechanical logic gate. This is really special for IIST because this work was done by one of your students. I know you have very distinguished alumni, also excellent students, Deepa and Banik, and of course Professor Ghosh. Because Professor Ghosh thought it will be nice to do with these arches mechanical OR gate, logic gates. So this was something that Deepa did at IIST. This figure that I'm showing you is your own product. And you can imagine, I'll not play the video because it takes a while. And later on, during this pandemic, when summer intern did the AND gate, now we got very bold. Now we are doing the entire logic processors using these things. So Professor Ghosh had that foresight to suggest this. Now we can do logic processors. And also we found somebody else had published a paper in not less than any journal like Science. They had a science paper where they had made miniaturized mechanical gates. We thought, why didn't we do that? Right? Because it's an interesting idea. So we're making entire logic processes using these negative stiffness elements. It's an AND gate. And universal gripper, I'm just showing the videos now. This video, as you can see, this uses a shell to grab things. It's a universal gripper. Shape of the object doesn't matter. The convex up one become concave, attached a few arms to it, and if you press it on an object like you see in this video, you can pick up anything. There is no magnet, there is no vacuum. You can pick up an object of any shape, anything, and that's what we are trying to do. Like a screwdriver is being picked up now. I hope the video is playing synchronous to my talking, and you press it again, it's a compliant mechanism, you can release it also. So this universal gripper, and what do you use it for? You can actually catch objects that fall on it. It just everts the other way, inverts, and we can capture these. Again, high-speed video where we can do, and there is an interesting application. I'll leave it to your imagination what big application you can pursue with this simple idea. And finally, I end with this vibration isolation, minus K. That's of negative stiffness. Somebody has started a company called minus K. Some of your labs might have their things. So this video, if I play, you will realize the power of negative stiffness. There is a wine glass where there is some colored liquid, not wine. And this minus K platform, if you do it, there is no sloshing anymore. So you would see the video where there is another wine glass, which is on a table, which is vibrating, a lot. And then you put this little thing. What that has is only negative stiffness element and a positive stiffness. If you put them in parallel, you get zero stiffness. And that simple thing that they have, a grand company is done. You might have used their vibration isolation. Many microscopes and other things are now using. I hope I've convinced you that there are a lot of gainful outcomes if you can exploit negative stiffness. I will end here, and if there are any questions, I'll be very happy to take. Thank you.
Okay, thank you, Professor Ananthasuresh, for your illuminating presentation of this lecture topics. Now we go ahead and take some time for question answering sessions. So now I would request the audiences to ask some questions to Professor Ananthasuresh. Please ask some questions.
Yeah. Good evening, Professor Ghosh. Thanks for joining.
Can I ask something?
Sure, Professor Malik. Yeah.
I think this negative stiffness vibration isolator, this person also did it from his PhD thesis, right? In 1995, deep lattice.
Yes. Yes.
He first did a PhD on this and then opened a company, minus K technology.
Exactly.
Now,
Yes.
this is almost used everywhere. When I tried to do it in IIT Kanpur, and Ashutosh Sharma says he has already purchased 6 of those. So I said, what's the point in making it?
Yeah. Right. But there's a lot of
What
details are
MTech
there.
student did, just the same thing to show that it works.
Yes.
If I may,
Suresh,
say
Yeah.
something.
I had one question.
Yes.
That what
Ghosh.
what is that this bistable switches and devices, how long they will perform? Because what will happen to the material which is continuously undergoing this kind of positive and alternate
No.
stages?
Fatigue. You are thinking of fatigue, is it?
Yeah,
Dr.
not
Ghosh?
fatigue only, not
Right.
only on fatigue, but even the various kinds of elastic coefficients, etc. Will they undergo change?
Yeah, I think that it requires very careful design. With metals, there is no problem with, in fact, they are shallow arches and shallow shells. So the deformation is not very high. Strains are not very high. So stresses are also low. So there is no problem with the fatigue because the tinlet I have it for 20 years and it still works. And surprisingly, the 3D printing material also has evolved considerably, as many of you would have used. Right, we this polyurethane thing that we are making this footwear, we are walking on it. My student is so confident that it's not going to fail at all. Material failure is not going to happen. So I think materials have come a long way. So I think there is less concern about they failing mechanically. So, but instability is what we need to control. That's more of our dynamics. So my earlier student Safan did the statics. Now the current student Priyabrat Maharan is doing dynamics of it. So if we do it right and control the negative stiffness region properly, then I think we can actually get them to work the way we want. Yeah, a lot of details. I could not present all those today.
No, that we all know. It's a wonderful work, and of course, I consider you as Thomas Alva Edison in the area of machine design.
Thank you, sir.
If you present your
Okay.
10 years or 20 years of work in one lecture, nobody expects that. Whatever
Now,
you have
Professor
exposed to
Suresh,
the
Professor
crowd,
Suresh,
Yes, sir.
if I may say something,
Yes,
is it,
Professor Raj, yes.
sir? I was considering. I never heard of negative stiffness. Honestly, I never knew. But today, in your 45 minutes lecture, you not only introduce the subject, you could make a layman like me appreciate the beauty of it. So I was drawing a parallelity, in electronics and all this, a Joule effect was found. Just the electrons rush through when the voltage certain level. So your work, it's a mechanical engineering work, but I was trying to compare it with that electronic Joule effect. This is something which has opened the door of beautiful technology. I hope it comes up with various kinds of applications, which it is a wonderful thing. I am a learned, before 1 hour, Achyut Ghosh 1 hour back is a much more learned man than Achyut Ghosh 1 hour later after hearing Professor Suresh's lecture. Thank you very much.
Thank you. By the way, I enjoyed your lecture also. I watched it completely. It was so inspiring. And you are right. In many fields, this instability is being exploited now. In fact, there was a Solvay conference which says, let's turn failure into success, right? Using this instability for this. My student Safan attended that. He was very inspired. Physicists, chemists, chemical reactions also have this
And
bistable negative
you
phenomenon.
started, sir. One more thing prompts me to say. You started with that uncomfortable thing for structural engineers for LYR, this failure, this LYR failure. So that was an uncomfortable thing in structural engineering. We try to avoid it in structural engineering. But here in mechanical engineering, we are using the same effect to betterment, to devices which helps human society. This is for a structural engineer. It's a great problem. For a mechanical engineer, this is an utility. It's a great thing. Thank you.
Professor Sarkar, I think you are muted.
Sorry. Yes, I agree with Ochudha. Dr. Suresh, you made a wonderful job in terms of starting up introduction of a subject very few people are aware of, and then took to the really height of the research area. Really appreciated.
Thank you.
Now, as a follow-up of Amitabhoda, I will have a question to you.
Mhm.
It is not necessarily the issue of fatigue alone. It is also the issue of wear, tear, and fretting. One specific example I want to follow through because that is close to my heart. I am also working on a different project where I am trying to follow through the diabetic shoe. Okay, I have a patent in that area. I'm not a patent. I take back. I have what you call record of invention. We are starting going through the process. The challenge, as a follow-up of what Amitabhoda said and Material said, is same thing. In case of a diabetic patient, what happens? These are very, very like a poisoning. It takes a long time to change the pattern of the so-called pediatric pressure on the shoe. So the question is that as the pressure changes, your mechanism what you use it today will not be valid anymore. So we need to check it every year or so. Now, it will be really nice if you can add a real-time sensor that will keep on watching how the pressure changes with time. And not only that, as a follow-up on that, you can use it as an indicator of the progression of the disease. Your system is wonderful, but what is missing in the whole picture is that real-time data transfer. If we can do it, that will be an indication that how the disease is progressing. What I did real in that case, we found a pattern where I say, of course, it was whole simulation. It's not the real deal. Okay, where you can see that by arbitrarily or by simulating a change in the pressure pattern, then you can find as a function of time whether the slope of the pressure time changes. That gives an indication that you can use it as a indication directly to the health care provider to tell him or her that time to intervene. So I really liked your approach, but I took a slightly different tack, but looks like there's an opportunity here. Thank you very much, and I will talk to offline later on. I have your email address. I'll talk to. But it's a wonderful presentation. I really appreciate, and I agree to Achyutan Amitabhoda. I really appreciate. Thank you so much.
Thank you, Professor.
And thank you, Vidyut, one more time. This is really, as Dr. Suresh said, it's a wonderful forum where totally different topics, totally different experts comes, and yet bring everybody get together to share knowledge and information. Thank you, everybody. Really appreciate it. Thank you.
Thank you, Professor Sarkar. I will talk to you about this idea. We
Yes.
are doing in-shoe pedography where you can measure it. And we had also made where you can see on your smartphone the entire plantar pressure with the sensor.
Exactly. That's what I'm talking about. Plantar pressure. Yes. That would have been really nice. Okay. And in real time. Time is a huge deal. Yeah.
Right. Yeah.
It takes 3 to 5 years. But question is that I don't know, in this part of the world, I live near Mexico and Texas. We are unfortunately the most obese and most diabetic prone county in the whole country. And obviously our people are very, okay, just like, it brings back my own memory when I was a poor undergraduate student. Okay, this and like that. Now, the challenge is that in diabetic is that what I call, you need, I call it DEMI. First thing is that D stands for your drug, or then E, exercise. D is for diet, exercise, medication, information. DEMI. If you don't have the DEMI, you are in trouble. What happens, most of the poor people, because of the lifestyle and because of their meager resources, they don't go for diet, they don't follow their drugs, don't do the exercise, and they don't have the information. So they die very fast. Amputation, leg amputation is one of the biggest thing here.
Yeah.
So I'm sure some of the things are happening in India too. Because the similar demography. So your device, if you done in real time, will do a wonderful job to intervene in time to avoid amputation.
Yes. Yeah. Just one comment that negative stiffness, that's the focus of today's discussion. Negative stiffness acts like a sensor in itself.
Yes.
Because the arch senses it and snaps through. So the sensor, and since it comes back, there is actuation. So actuation is the person's force itself, weight. So without sensors, eventually, we need sensors to design our device and calibrate it and do it all. But eventually, it will be all mechanical footwear. With any material that can sustain these stresses, we can do it. The idea, so that it can
Devices
reach
are
out to
wonderful.
people.
They are wonderful. Only the missing part is from the electronics part. Communication is the real time. The time domain is missing.
Yeah.
Once you have introduced that one, then we got all the things. Thank you.
Great.
By the way, I like your chair too. I don't know. Maybe I'll be interested to see if we can sell it here.
You'll be using one of those chairs?
Yeah, sure. Actually, the company is working on it, and they're very serious about translating it entirely. And we are they're manufacturing these shells in bulk now. So that's all. My work ended. Now they are doing all the hard work.
So you are a teacher.
It's one of my former students who is started a company with this. Yeah.
But I hope when they get a full company running, they give funding to your organization.
Yeah. Right. Yeah. Thank you.
The company is now in incubation stage. It's already.
Are you
Yeah, it's
also
incubated
coming?
in IISc itself. Yeah. It's
Suresh, are you coming to LA area in September, which was?
September, maybe not. Maybe little later. Yeah. So after he settles there. Yeah.
Okay.
Yeah. If we change our mind, I'll let you know, because you are there. It'll be glad to meet you there as well.
I'll be there till end of October. So maybe if you are there, we'll surely meet.
Yeah. Day after tomorrow, I'm coming to Kolkata, so I'll be meeting Professor.
Yeah, as you wrote to me. I think you will meet Ashok most probably.
Yes. Yeah.
অমিতাভ, তুমি কেমন আছো এখন? How are you, অমিতাভ?
কেমন দেখছো তুমি?
তোমার
কালকে
দাড়িওয়ালা
রাত্রে একটা
দেখছি।
লেকচার ছিল আমার। That
তুমি
was
একটা-
an inaugural
হ্যাঁ।
talk of some conference in IIT Kharagpur, and that I had to give from 12:45 to 1:30 that night. So I was a
Bad
little late
timing.
in getting
But
up.
you have to shave. Amitabh, you have to shave before that. They will throw your picture in the screen in the audience.
No.
Sorry for the off-the-line question. Amitabh, you are in Austin now?
Yes, I'm in Austin.
Good.
I came here almost a month back, Kamal. So how is your
Good.
wife? Her knee,
Oh,
she said that
she is fine. That's why I was asking for the chair. By the way, my wife has a total knee surgery. So it's one of the challenge for her is to stand up. Okay. So if I get the chair, I'm ready to buy it.
Okay. I'll convey to my student. Yes.
One order is booked.
Yeah.
very
I think the
nice.
record is still going on. Maybe we need to stop that. If the
Yeah. Yes. I think. No.
Well, our students and scholars have any queries?
I'll take leave since I'll prepare for my visit to the airport. Thank you.
yeah. Thank you, Professor Ghosh.
See you, Achyuta. Well,
Okay, Suresh, see you
Yeah.
later then.
Thank you. Bye,
All the
everyone.
very best and thank you very much because it is my alma mater and this is the department where I started teaching in
Yes.
65 May. It's
Right.
a long teaching career I had.
Yeah.
Okay, thank you very much
Thank
for
you.
kindly giving this
and
wonderful
on behalf of the
talk.
department,
Yeah.
let me also thank
Thank you.
Professor Ananthasuresh for this nice talk. Yeah, it's a very nice presentation, starting from the little examples to these complex mechanisms with chairs and the souls. That's really nice. Wonderful, wonderful job your team is doing.
Thank you,
Let me
Professor
also
Ghosh.
take this opportunity. Yeah, let me also take this opportunity to thank our today's chair, Professor Shishir Go, for taking time off to chair this session. Thank you, Professor Go. We had a
Thank you.
nice time, very nice time. So maybe we can now call it a day. The recording can be closed. Yes, I have another responsibility on behalf of the Centenary Celebration Committee. Let me present this certificate as a token of appreciation to our today's speaker. This is a digital copy. We'll be sending it through mail. We also have a hard copy, and that we'll be sending along with the memento.
Thank you.
Thank
Oh, thank you very much.
Please accept it.